In this section, we're going to look at some design choices when implementing balancing, and it's really more design questions that need to be answered because I don't actually answer the questions for you. I just point out what these questions are that need to be addressed. When we're looking at what is cell balancing or what is a balanced battery pack, there's a definition by Davide Andrea, who's one of the pioneers of battery management systems. He says a balanced battery pack is one in which at some point in its cycle, all of the cells are at exactly the same state of charge. A balanced battery pack is one in which at some point in its cycle all of the cells are at exactly the same state of charge. There's other definitions that are possible where this condition is never actually met, and that's okay. This definition, though, is going to be sufficient for now, and there are more advanced topics, I guess, that we could consider at some other time. But what should that state of charge be? And we consider a couple of different options. One of them is to balance all cells so that when one cell is at 100% state of charge or at the top state of charge of the design limit, then all of the cells are also at that top state of charge. So in terms of this picture, what we're trying to show is this is not state of charge versus time so much as notice the horizontal axis is 4 different cells in the battery pack with a strong cell and a weak cell and 2 medium cells. And the size of the bar indicates the state of charge range used by that cell over time. So the top state of charge is our top design limit, and then this lower line here is the bottom design limit for state of charge. And in this example, we're imagining that when one cell is at the top state of charge, all of them are, and then as I discharge the battery pack, as I'm using it, the strong cell is going to discharge most slowly compared to the other one. So the weak cell is going to discharge most quickly and so forth, and the weak cell is going to use its entire state of charge range, whereas the strong cell will use the smallest state of charge range because it's stronger. If we choose to balance at the top state of charge, remember that voltage, the open circuit voltage of a cell, depends on the state of charge, and at high states of charge the voltage is higher than at low states of charge. And so for the same current, the voltage being higher means that we are getting basically more energy is stored in this battery pack. So for the same number of amp hours, I get a higher voltage. So this is good for electric vehicles. If I want to maximize range, I want to cram as much energy as I can into this battery pack, and this is probably, this is at least something I might want to do. However, some of the aging mechanisms we looked at very briefly in the previous chapter are accelerated when the cell is at high states of charge. That means that this pack will spend more time at high state of charge than a pack that is not balanced at the top state of charge, and so it will age more quickly. So there's a trade-off. We could balance at a midpoint state of charge, and that's what we're trying to show in this picture here. So when, suppose the midpoint is 50%, when one cell is at 50% state of charge, then they all are at 50% state of charge, meaning that the strong cell does not really go very far away from 50% state of charge ever, but the weak cell still experiences its entire range because it's the weaker cell. The cells are not at as high a state of charge range as in the previous case, so the voltages are not going to be as high, so there's going to be some impact on the energy storage capability. But some applications like hybrid electric vehicles are really not very sensitive to how much energy you store. Instead, what we're doing here is, in some sense, we're maximizing the ability to accept or deliver power because there's some room here between the most of the cells in the battery pack and a design limit, and so those cells could deliver more power. Of course, if the weak cell is the one that's always limiting the power, then that doesn't actually help a whole lot. But hybrid electric vehicles tend to operate more in this mode than they do in this mode here. We've considered balancing at the top, balancing at the middle, so let's think about balancing at the bottom. We would have lower energy because the cells would be at lower voltages, lower states of charge. But it does minimize some high state of charge based aging. Notice this cell is never at high state of charge. This one stays pretty far away and so forth. But this might actually be counterproductive, which is kind of weird to think about it. But because the strong cell is the one that stays away from high states of charge the most, so it will remain strong longer, but the weak cell is still operating at high states of charge, so it will get weak just as quickly, get weaker just as quickly as the other cases. So this one here, the strong cell stays stronger, the weak cell gets weaker, and it in fact accelerates divergence among the cells in the battery pack, and it makes the imbalance condition worse. So I'm not going to make decisions for you as to which balance point to use, but I can't really see any reason why someone would choose to use that balance point in an application. A final alternative, if we're using fast active balancing, the set point for every cell where all the cells have the same state of charge is in some sense dynamic, and it's really that basically, at least one way of doing active balancing would be to balance every cell all the time, so that at every point in time all cells have the same state of charge. It's not the only way to do active balancing, but that's one way to do active balancing. So when all cells are at 75%, or when one cell is at 75% of state of charge, then all of them are. Well, how do we actually do that? Well, we're moving charge from a strong cell into a weaker cell. So I'm moving charge from that cell to that cell, and to some extent from that cell to that cell, and so forth, and maybe even into this cell. But we're moving charge around, and in order to do that, the weak cell ends up taking less of the load, and the strong cell ends up taking more of the load. And because the strong cell experiences a greater total load or more stress, it tends to age more quickly than the weak cells do. So if somehow we have a weak cell because it's aged that way, and we have a strong cell because it hasn't aged, we're actually causing the strong cell to age more quickly, the weak cell to age more slowly, to bring the cells into a more homogeneous sense, so that all of a sudden the pack is not only balanced more, but in terms of the instantaneous state of charge of the pack, but it's also balanced more in terms of the strengths of the cells. So this is a self-regulating effect, which is kind of cool. So there are some benefits to being able to do fast active balancing. And again, these are design choices. Which one of these four do you choose? There's not an answer that's going to fit every scenario. As a controls engineer, you're going to have to consider what are the advantages and disadvantages of each one of the alternatives for your application and decide which one to use. If cost was not an issue, probably we would always choose this, but active balancing is quite a bit more expensive to implement than passive balancing. And you're going to do a project where you may actually conclude that active balancing is not really necessary. So you have to decide, should I do active? Should I do passive? If I do passive, which one of the balance points do I select, and so forth. That's where do I balance. And then at a point in time, which cells do I balance? Which cells do I remove charge from? Which cells do I add charge to? Which balancer circuits should be switched on at any point in time is what we're thinking about now. So we could choose to balance based on a state of charge estimate until the difference in states of charge between the different cells is small. Now we will never have a case where our estimates are exactly the same for every cell because there's noises. We've seen there's error bounds on our estimates. So we wouldn't balance until our delta state of charge was 0, but until they were within some acceptable range of a few percent, maybe. However, if our state of charge estimates are poor and noisy, we can balance the wrong cells. We can think, oh, cell number 2 needs to have charge removed because I have a bad SOC estimate. So I start removing charge from it, but in fact, that wasn't what I was supposed to do at all, and the SOC estimate corrects itself maybe, and then I realize, oh, so now I have to balance all the other cells because of that bad SOC estimate. So even if all cells are exactly the same, if a bad estimate says I need to knock that one down, and I do, then all of a sudden I've got an out-of-balance pack, and I have to knock all 3 of these down to get them in balance again, is the idea. So a poor state of charge estimate and balancing based on that state of charge estimate is going to lead us to do the wrong thing. We could also choose to balance based on just a voltage measurement. It's a lot more reliable than a state of charge estimate in terms of its accuracy. I might have a 16-bit A to D, probably not, but probably at least 12-bit analog to digital converter. And I'm not doing any more processing on it than that, except maybe you'd want to filter it to average it a little bit before you balance based on a voltage measurement. But basically, there's not the complexity of something like a Kalman filter operating on the voltage measurement, so it makes it quite straightforward to compare voltages and see which is high and which is low. Voltage, we've seen, though, is a poor indicator of state of charge. Just go back to the Tino method of estimating state of charge and realize it's not a very good indicator of state of charge. I might have different resistances. I might have different time constants in the cells or whatever. So that if I balance a high voltage cell at this point in time, that might not be the right thing to do. It might just be a high resistance cell that I should have waited and balanced a different cell instead. We could even balance based on the total available energy. Total available energy is an interesting quantity. It's saying it's not the total energy in the battery pack. That's different. The total energy we saw back in Chapter 1 that said if I extract every electron, if you will, out of this battery pack before I get to a minimum state of charge limit for all my cells, that's how much energy I could get out. Available energy says this is how much energy I can get out while still meeting my design criteria. And my design criteria usually have a power requirement as well. So if you think of this as the total energy limit of a cell, the available energy operates inside this limit because I can't go above some state of charge and have total regen power available, and I can't go below some state of charge and have total discharge power available as well. So in order to maximize total available energy, we have to take this power design criteria into account and realize that high resistance cells are going to limit power. I'm going to hit either a charge voltage or a discharge voltage more quickly with a high resistance cell than others. So I mentioned this a little earlier in the previous section, but we might actually take a strong cell and a weak cell, and over time the strong cell would have its whole range, but the weak cell, we would have a different range. We would bias the states of charge to be different so that the weak cell could still have maximum power here when the strong cell still had maximum power, and the weak cell would still have maximum discharge power while the strong cell had the same discharge power. So here we're maximizing energy that we can extract from the battery pack before this design limit on cell voltage, or based on a power requirement, is exceeded. So we can improve this available energy by moving charge from a low resistance cell to a high resistance cell in order to, in this case, we're thinking of this scenario, the discharge. So I'm bolstering or artificially increasing the SOC of the high resistance cell so that at the end of the discharge, both of them hit the power limit at the same time. So to do that, we need an accurate cell model and an accurate state estimate for every cell that also estimates resistance and power capability quite well. So we could do all of those things. Which one do we do? It's going to depend on your application. You have to decide which of these criteria is most important for you. Balancing based on voltage is going to be the least expensive, but probably the most wasteful. Balancing based on state of charge is less wasteful, but you have to have a good state of charge estimator. Balancing based on total available energy is going to require active balancing circuitry, so it's going to be the most expensive, but it's probably going to give you the most range out of your battery pack, so that might make it worth it. And then lastly, when do we balance? We could balance all the time, whenever the battery pack is turned on. And this is needed for a hybrid electric vehicle kind of application because we never have a plug-in operating mode. And so there's never really a difference in activity for hybrid electric vehicle. It's always operating in the same mode, so I just always balance. And if I'm doing fast active balancing, I also have to balance while the pack is on in order to maximize available pack energy and power right now. This is harder to do right, to balance all the time, because SOC estimates must be accurate even in the face of a very dynamic load profile where voltages and currents are changing quite a lot. If I have a plug-in application where I've got a very controlled charge versus the dynamic of driving, so electric vehicle, plug-in hybrid, or extended range electric vehicle, it may be smart to balance only when you're charging, because the charging is a much gentler scenario. I'm just doing constant power or constant current. It's easier to estimate state of charge well when we're doing it. And it's also dissipating, assuming I'm doing a passive balancing especially, it's dissipating the difference in energy between cells only when I'm plugged in, and I can recover that energy from the wall power. So no matter how I do passive balancing, I'm going to dissipate energy. Understood, I'm not getting perfect efficiency, but if I do it when I'm plugged in, I can recover the energy, not in the sense of creating it again, but in the sense of being able to fully charge the battery pack and have maximum range. Also, some of the balancing circuits generate quite a bit of heat, and that requires the thermal management system of the battery pack to be able to handle the added heat. And it can be considerable. It can be on the same order as the heat generated by the cells when they're operating. So to be able to ramp up my thermal management system when I'm plugged in is a big advantage, because that's going to take energy as well. And if I can get that from the wall rather than subtracting it from the vehicle range, that's a big advantage. And then third, which is some combination, is a predictive balancing. So here I'm thinking of I charge first and then I balance the cells at the top of charge. That's the easiest thing to do. The predictive balancing, I could do it while I'm plugged in which case I'm balancing the cells while I'm charging. I'm balancing them individually by predicting where the end point is going to be for every cell when I'm charging it. So we're proactively balancing even when the state of charge right now of all the cells might be the same, but I realize that when I fully charge the battery pack, if I don't do anything, the states of charge will be different. I'm going to do the balancing right now to make sure that I have the shortest balancing time. So this here takes longer because I charge and then I balance. This here can take longer because I'm shorter because I'm charging and balancing at the same time. So those are some thoughts of what design decisions need to be made when we're thinking about some of the control aspects of balancing. And of course, we haven't even talked about the electronics of how do I do balancing, and that's what we're going to look at over the next several sections.